Okay, so we're going to do a couple of examples using the closed interval method that we discussed in the previous section. So the first one, we want to find the absolute maximum and minimum values of the function y equals x plus 1 over x on the interval from 0.2 to 4. Now notice you have to have a closed interval on which we're looking at this function. And that closed interval has to be a part of the domain of that function in order to use the closed interval method. We wouldn't call it the closed interval method otherwise. So what we're going to do is first look for critical numbers on the open interval 0.2 to 4 for this function. And again, what that means is we first differentiate it, y prime, and this is an easy derivative that's equal to 1 minus 1 over x squared, just using the power rule. And then we set that equal to 0, okay? If this is equal to 0, I can add my 1 over x squared to both sides. I get 1 equals 1 over x squared, which is equivalent to x squared equals 1. Now the solutions to this thing are plus or minus 1, right? It has two solutions, plus or minus 1, but I can get rid of the negative 1 because I'm only interested in values that are in the open interval from 0.2 to 4. Negative 1 does not live in between those two numbers, but positive 1 does. So my only critical number in this interval is x equals 1, okay? Now, I also have the outputs of the endpoints of this function to consider. So that's 3 values that I want to plug into my function. I want to plug in the endpoints. So let's call this f of x so I can show the input there. What is f of 0.2? F of 4. Those are the endpoints. I'm plugging them into my function. And then also, what is f of 1? That's the critical number that I found. Well, f of 0.2. 0.2 is the same thing as 1/5. So if you think about that, x is 0.2 plus the reciprocal of 0.2. The reciprocal of 1/5 is 5. That's equal to 5.2. Now let's plug in a 4. Plugging a 4 into this function would give me 4 plus the reciprocal of 4, which is 1/4. That's 4 1/4, or 4.25. Finally, let's plug in a 1. That's 1 plus the reciprocal of 1, which is just 1, 2. These 3 numbers are the only possible candidates for my absolute extrema. So it must mean that the smallest value, 2 in this case, is the absolute minimum of this function on this interval. You can verify this if you go and graph this function in Desmos or your graphing calculator or something like that. You will see that at the value where x equals 1, within this interval is going to give me the lowest point on this curve. 5.2 is the largest value in that list. That makes it the absolute maximum. Okay? So done. That's the closed interval method. Let's look at an example that comes from an actual application. So in this one it says, after an antibiotic tablet is taken, the concentration of antibiotic in the bloodstream is modeled by this function here. C of t equals 8 times e to the negative 0.4t minus e to the negative 0.6t, where t is time measured in hours and c is measured in micrograms per milliliter. What's the maximum concentration of the antibiotic during the first 12 hours? By saying during the first 12 hours, that means that we're talking about the closed interval from 0 to 12. Hours is t. T is my input, and this interval represents an interval of the a subset of the domain of our function. It represents inputs. Okay. So to use my closed interval method, I first need to find the critical numbers of this function, which means I need to find c prime of t. All right, so for c prime of t, that would be equal to 8 times negative 0.4 e to the negative 0.4t plus 0.6 e to the negative 0.6t. That's an easy derivative to take, all right? We're going to set that equal to 0. Now I have a product of two things, 8 times this sum of exponential functions, and that's equal to 0. 8 is obviously not equal to 0, so I just need this guy to equal 0. Negative 0.4 e to the negative 0.4t plus 0.6 e to the negative 0.6t equals 0. I'm solving this. Okay, I can add that to both sides, so I get 0.6 e to the negative 0.6 t equals 0.4 e to the negative 0.4 t. What I can do now is divide both sides by 0.4. So 0.6 divided by 0.4, which is 3/2 after simplifying. And then multiply both sides by e to the positive 0.6t. That will cancel this guy out. E to the negative 0.4t times e to the positive 0.6t. I can add the exponents and I get e to the 0.2t. Okay? I can solve this using natural logarithms. After a couple of steps, it's pretty easy to find that t is equal to the natural log of 3/2 divided by 0.2. Do the algebra. It's just a couple of steps to get here. This I would plug into a calculator. I really want a decimal to look at because I'm going to compare this to other values. This is approximately 2.027. Okay? What I need to do now, that's the only critical number that I found. Notice I only found this number from solving this equation. So I have one critical number and I have two endpoints to check. I need to compare C of 0 to C of 12 and also compare C of this number, 2.027. Given the nature of this function, I would just use a calculator for this part. C of 0, that's an easy one. You can do that one in your head. That's actually 0. C of 12, here's my function. I would be plugging a 12 in for the t's here, but to use a calculator, that comes out to about, I'm going to say approximately, 0.0598. Okay? This guy, the one critical number that we found, if you plug that back into your function, you end up with, did I plug that one in? Yeah. Oh, no, I didn't. Hold on. 2.027. Okay, I forgot to plug that one in before. Just did that in my calculator. This one works out to approximately 1.185. Notice that that's the largest value in that list. That makes it my absolute maximum. 0 is the smallest number in the list. Absolute minimum. Okay? And that answers that problem or that question, and that also finishes 4.1.